to you and you're good to go.
Yeah,
Whatever.
Go for
Yeah.
it.
Yeah. Okay.
Okay, let's start.
Okay, we'll get right into it. So I'm going to go over the first question and Henry's going to do the other two. So question number 1, we have this section that they've given us, 610 UV 101 from grade 300 plus steel. Are you guys familiar with one steel at this point? You guys all know what one steel is and you have access to it and everything? Okay, if you don't, please get access to it, because if you don't, you might struggle. But basically, you can look up that section in one steel. UV stands for universal beam. So you want to look on the universal beam page and it'll give you all the section properties and everything for this specific section. So part A is asking us for the tensile capacity. So when they say tensile capacity, can you guys see this? Yeah? When they say
Maybe try a dark color.
a dark color, yeah. When they say tensile capacity, that means this thing, N subscript T. So for N subscript T, your tensile capacity for steels, you have 2 ways that a steel can fail in tension. So one of them is failure by gross yield. And the second way that it can fail is net fracture. So they don't specify which way it's going to fail in the question. So generally you would have to test both of these failure modes and just based on that figure out which way your steel section is going to fail. So for gross yield, this is the formula for tensile capacity. NT equals to AG Fy. And for net fracture, your formula is NT equals 0.85 KT AN F subscript U. So we want to find NT using both of these formulas and then we can compare them. So AG is your gross cross-sectional area, so the cross-section of the steel section that they've given us there. And you can get this from one steel. So if you look up the section that they've given us, the 610 UV 101, and you go to the UV page, then you can find that AG for our section is going to be 13,000 millimeters squared. So that's easy. Then Fy, that you can also find from one steel. And for this one, your section has both the flange and a web, and they both have different values for Fy, which is your yield stress. So what you want to do is you actually want to take the minimum of those two. So you'll have a separate stress for your flange, and you'll have a separate one for your web. So just again, looking up from one steel, for your flange, you have a yield strength of 300. For the web, it's 320. Obviously, the minimum of these is 300, so we're going to take our yield strength as 300 MPa. So that part is also done. So now we have everything we need to find NT by the gross yield. So we just want to put that into the formula. So our tensile capacity will be the area times the stress, and that gives you 3.9 times 10 to the 6 newtons. If you want, you can convert that to kilonewtons. So that will be nearly 4,000 kilonewtons. Does anyone have any questions so far? Good. Okay. Do you guys want a second to write that down? Are you okay? I'll keep going. So we want to now do the same thing for the net fracture. So we've got 3 more things that we want to find: KT, AN, and F subscript U. So KT they have actually given for you in the question that KT is going to be 1. If you don't have KT given to you though, you can take it from clause 7.3 in AS 4100. So that's just if it is not given, you would just go to that clause, look it up, and find it from there. AN is your net cross-sectional area. And this one you can't find from one steel. So one steel only gives you the gross area, which we looked up before. But for this question, they've said that we can just assume that your net cross-sectional area is 0.9 times the AG that we had before. If you don't have this assumption, then you would have to calculate AN yourself. And the way you do that is it's just going to be the gross cross-sectional area minus the area of any holes or other like penetrations that you would have. So I'll just put that in brackets. This is what we've been given. This is just if you don't have that assumption, then you have to calculate it for yourself. Okay, the last thing that we have in this formula is F subscript U. This one is your tensile strength, and this is also from one steel. So it's not in the table, but if you look at the bottom of the page, in the notes section at the very bottom, then you can find the tensile strength. And for the section that we have here, it's going to be 440 MPa. So now we have everything we need for this formula. We can just put it all together. So our net fracture strength will be 0.85 times KT, the reduction factor, and times your net cross-sectional area, which is going to be 0.9 times AG, which we found before. And finally, times your F subscript U. And when you put that all in the calculator, you should get this much. And if we convert it to newtons, that'll be 4,375.8 kilonewtons. Any questions on that one? Cool. So now we found the tensile capacity using both of the failure modes, gross yield and net fracture. We want to take as the overall tensile capacity the smaller one of these two, because the smaller one means that that is the failure mode that you'll have first. So that is the one that we want to take. So our overall NT is just going to be the minimum of those two. So the minimum of 3,900 and 4,375.8. Obviously that would be 3,900, so this is going to be our tensile capacity for this section. And that's your answer for part A. Any problems, questions? Do you guys want a second to write that down before I rub it off?
Do you want to take a break with it?
Yeah, sure. Part B is asking us for the same thing but now for compression. So we want to calculate the compressive capacity. So when they say compressive capacity, that would be this thing, and subscript C. And this one, there is just one formula for it, so we don't have like separate failure modes like we did for the tensile. And your formula for NC is going to be alpha C times N subscript S. So these are two things that we need to find. N subscript S, what that means is this is called your nominal section capacity. And this one has a formula of its own. So the formula for nominal section capacity is NS equals to KF times AN times F1. And we'll do this one over here. For alpha C, this is called the member slenderness reduction factor. So this should be smaller than 1 or equal to 1, and it should reduce your capacity. And you get this one from a table. Specifically, you get this from table 6.3.3C in AS 4100. Okay, we'll come back to the nominal section capacity first, and then we'll go ahead and do alpha C. So for the nominal section capacity, we need KF. So KF is called the form factor. And this is another one that you can get from one steel. So if you look up your section 610 UB 101, you get the form factor as KF equals 0.888. Then we have this AN, which we've already seen before. So this is our net cross-sectional area. So here we haven't been given any assumption for finding out what AN is. So we can't use the assumption AN equals 0.9 times AG. But what you can do is you can use a different assumption, which is just that your AN is approximately equal to AG. And then you can just use AG wherever it says AN. So the condition for using this assumption is like this. So if your reductions that you're making due to like any holes or penetrations is, it has to be less than this much percent, so 100 minus F subscript Y over 0.85 F subscript U %. So this is really easy. Both of these you can get from one steel, F subscript Y and F subscript U. You can just put this in your calculator super quickly, and if your reductions are like less than this much %, then you can just use this assumption. So for this question, it's fine. We can just assume that AN is approximately equal to AG. Okay.
Sorry,
And
what's
then-
that term in the numerator? Is that Ly?
FY.
Fy?
Any other questions? No? Okay. FY we had before. That was from one steel. And we already found that that is equal to 300 MPa.
Wait, how do you go to KF 0888?
This is from one steel. It's at the bottom, so if you look at the notes in one steel, it's not in the table itself, it's at the bottom of the page. Oh, sorry, this one should actually be in the table. Sorry, that was the different one that was at the bottom. Do you want me to, do you have it up? Would you like me to?
It's at on 0.85. 0.9.
Do you want me to have a look? Oh, okay, yeah. This is a different one. This is KT, not KF. Yeah. One steel, you want to use this table, this kind of table. This is AS 4100, so that's a different standard.
Oh, it's KF.
Yeah,
Ah,
yeah, this one. That's right. Yeah.
Oh, you got another question?
Oh, yeah.
Sorry, that condition there where AN is approximately equal to AG,
Yes.
is that from AS 1400?
Yes.
Okay. Do you know which course?
I don't think I have it in my notes. Let me have a look.
It's definitely in the lectures.
Yeah, it should be in the lectures, otherwise I wouldn't have it.
Yeah. I've definitely seen it.
Yeah. Just have a look in like your compression members lecture.
Was it a comp?
It's a beam, universal beam.
So KF's down here, I think.
Yeah. Yeah.
Which size was it?
It's a 300 plus 610 101. Yeah, 0.88. Guys, also be careful when you're using one steel because there's two separate kinds of steel. So you have your 300 plus and then you have the 350. So the 300 plus is on the left side of the table, so you want to look at that part of it. On the other side, you have the grade 350. So that's like something different. Don't look at that because it'll give you like different values. Just be careful of that.
Yep, I'll switch back to this.
Thank you.
Yep, no, we're good. We'll leave that.
Any questions? Any issues so far? Okay, we can keep going. So now we have everything we need for the nominal section capacity. Let's calculate that. So that will be NS equals to KF, which was 0.888, times AN, which we'll take as AG, which we had from one steel before was 13,000. And Fy, again from one steel, is 300 MPa. So this is equal to 3,463.2 kilonewtons. So this is your nominal section capacity, so the first part of the formula that we need. Let's come back and do alpha C, which is your reduction factor. So for the reduction factor, which you get from this table in AS 4100, you need two things. You need your slenderness, and you also need to know this other constant, which is called alpha B. So we need to find what these two are, and then we can use the table to figure out alpha C. So for the slenderness, we want to find it in both the x direction and the y direction. Because for a compression member, you can have stuff happening in both of the directions, so it can buckle both ways. So it's important that we test both directions because you don't know which way it's going to fail. To find the slenderness, this is the formula. So you need your effective length, and you need this R, which is called the radius of gyration. You need KF, which we've just found before, and you also need Fy, which we also found before. So let's get these two. LEX, that is your effective length in the x direction. And in this question, it's actually been given to you that the effective length in the x direction is 4 meters. Or you can also write that as 4,000 millimeters. Rx is your radius of gyration, and this one you can also get from one steel. And that gives you a radius of 242 millimeters for the section that we're looking at. So we can put this all into the formula. That'll be 4,000 over 242 times root 0.888 times root 300 over 250. When you're looking at the length and the radius here, it doesn't matter what units you use, just as long as they're both the same so that they'll cancel out. So they can both be meters or they can both be millimeters. Just make sure you don't have like one in meters and one in millimeters. It's just got to match. So this will give you a slenderness of 17.06 in the x direction. So we'll just repeat this same process in the y direction. So again, we've been given the effective length. In the y direction, they've said it is 2 meters or 2,000 millimeters. And our r, we can again find from one steel, same as with in the x direction. And that will be 47.5 millimeters. So if you put that below the formula, it's 2,000 over 47.5 times 0.888 times root 300 over 250. And that should give you a slenderness of about 43.46. Any questions up to here? So now we have two slendernesses. Which one do we want to use? In this case, we want to take the maximum one. So the bigger of 17.06 and 43.46. Obviously 43 is bigger, so our final slenderness we're going to take as 43.46. So now we've found the first thing we need to use this table. Now we also want to find alpha b. I'll write that up here. So for this one, again you want to use a table. This one comes from table 6.3.3b in AS 4100. So that's the table that gives you alpha b. There are two separate tables that you can get alpha b from. The reason that we use this one is our kf, 0.888, is obviously smaller than 1. So there is a separate table that you would use if your kf is equal to 1. And that would be table 6.3.3a. So just be careful which one you're using. So from this table, all we need to know is what kind of section is it. So it's given to us, like our section is obviously a universal beam. So just reading off the table, we'll have alpha b is equal to 0. Any questions? Okay. Right. Oh, can you guys see if I write over here? Yeah. Okay. Now we have our alpha b and we have our slenderness. So we want to put them together and figure out what our alpha c is going to be. But the problem is this table 6.3.3c, this only gives you values for very specific values for the slenderness and the alpha. So our slenderness here is like a weird number. It's not like a nice number, it's like 43.46. So what you want to do in this case is you can't just round it and hope for the best. You want to find the two values that it's closest to. So the table will give you a value for 40 and for 45, although not for 43.46. And from that table, you will get AC equals to 0.905 for slenderness of 40 and 0.884 for a slenderness of 45. And these are both from this table. So what you want to do now is just use linear interpolation between these two numbers to figure out what alpha C would be for our slenderness, which is 43.46. And that would be approximately 0.89. And this is done just using like linear interpolation. So just don't like round it up to 45 or down to 40. Just make sure you're actually like looking for a value that's in between those two. Does anyone have questions on that? Okay. Now we have everything we need to find the actual section capacity. So that was alpha C, which we found was 0.89, times the nominal section capacity, which we found up here. And that should give you 3,082.25 kilonewtons. And that's your answer for part B. Any questions there?
Where did you get lambda and 40 from?
Here?
Yeah.
So our value is 43.46, but the table doesn't give you that number exactly. So 43 is between 40 and 45. That's why we use these two numbers, because then we can find something in between.
For the table, why the first one is just C and then the second one is B?
This one is used for alpha B, and this table is used for alpha C.
So the same alpha B there?
This one's for alpha C. Table C is for alpha C. Table B is for alpha B. So they're two separate
alpha B
things.
are the same?
Alpha B and alpha C are not the same. So you need alpha B to find alpha C. I know it's confusing. Does that make sense?
No.
So this table here, table C, this gives you your value for alpha C. But to use that table, you need to know what alpha B is. So to find alpha B, you have to use a separate table. Yeah? Yeah? Have a look at the tables in AS 4100, because I think that might make it a bit clearer. Did you want to take another photo
Oh, yeah.
before I run it off?
Yes.
Thank you. Okay, so the key thing for this part is that our connection is using bolts, and those bolts are in shear. So, and they are asking us to find maximum axial capacity. So what they want you to find is this thing, V subscript F. And there are different formulas for V subscript F, and the one that you use depends on like your type of connection and how it is connected. So they've specified that it's going to be in shear. So your formula for bolts in shear is 0.62 F subscript UF KRD KR and subscript N AC plus N subscript X A0. Now this part you can always take as going to 0. So we only want to worry about these 5 things over here. And again, just be careful which formula that you're using, because there is a separate formula for bolts in tension. This one is for bolts in shear, which has been given to us in the question. So we want to use this one. Okay. F subscript UF. This is the minimum tensile strength of the bolts. And you can get this from AS 4100. So this can be found in table 9.2.1. And if you read off the table, it depends on the type of bolts. So in the question it says 8.8 S bolts. So just looking at the table, for this specific type of bolts, your strength will be 830 MPa. Okay. KRP, this is a reduction factor. But it only applies to a specific type of bolt. So it only applies to bolts that are 10.9 volts. So ours is 8.8. So we don't need this reduction factor. That means that we can just take KRV is equal to 1. KR has been given to you in the question. So that will just be 0.9. And then we have AC, which is your area. This one also comes from a table. This comes from table D1 in AS 1275. So this is a separate standard to AS 4100. D1D means it's in Appendix D. And this also depends on the type of bolts. So in the question, they've said that they are M20 bolts. So for M20 bolts, just reading off that table, you will have an area of 225 millimeters squared. So now we've got everything in this formula. Let's find the force for 1 volt. So for 1 volt, that will be 0.62 times 830 times 1 times 0.9 times 225. And that should give you 104.2 kilonewtons. So this is for 1 volt, but the question says that there are 40 volts. So to get the value for all 40 of them, you just want to multiply this by 40. And that will give you 4,168.26 kilonewtons. And that's your answer for part C. Any questions here? Yes.
So why is NX always
0. You can just always take that as 0. Yeah. Yeah. I think that's right, isn't it? Yeah. So yeah. I don't think I've ever seen it like actually included as not 0. Yeah. The part in the brackets. Oh, here. Wait. Let me rewrite that. So this would be, because we're just using 1 volt, and subscript n would be 1. AC we found before is 225, and you can assume that this second term is 0. So it's basically just multiplying by 225. Any other questions? Yes?
What do you mean by when you say it only applies to 10.9?
So there are different types of bolts. The type of bolt that we have here is 8.8. You can see that in the question it says 8.8 volts. There is another type of bolts which are 10.9 volts, and so this reduction factor only applies to that. So if you have 10.9 volts, this value instead of being 1 will be something smaller than 1. And you would have to find that separately.
Thank you.
All good. Any other questions? Do you want to take a photo?
Yes.
Okay, last part for this question. They are saying that in part D, we're going to replace the section, which was previously a universal beam. We're going to replace that with a universal column. And when they say determine the minimum weight of the section, they're basically asking you which universal column are you going to be using. So it's up to you to choose one and make sure that it satisfies like whatever criteria you want to satisfy. So here they've said we want it to achieve the same compression capacity. Oh yeah. Oh yes, sorry. Yeah, of course. So we want this to achieve the same compression capacity. So we first of all want to resize our column. Resizing means we want to find what the new area should be. So this is the formula for resizing. Is that okay, or do you want bigger? So the formula for resizing is going to be like this, so n star over 0.4 f subscript y. So again, we just want to find out what the different things in this formula are and just put them in to the formula. So here, let's start with Fy. This is actually going to be different to the one that we've been using before, because they have also said that we're changing the type of steel. So here it says AS NZS 350. This means that we are now changing to 350 grade steel, which was on the other side of the table. So our new Fy will be 350 MPa. And N star, we can assume, so you guys have all seen the like N star is greater than, or sorry, smaller than or equal to, you guys have seen this before, right? So we can just assume that these two are equal while we're doing the resizing. And because we're going to check it over at the end, it doesn't matter if you make like small assumptions at the end. Okay. So we can put in all our values. Oh, firstly we need this one. This is the safety factor. The safety factor depends on the type of material and also how the member is being used. So for this one, this is obviously steel and it's 4 bolts in shear. And you can find this from a table. So it's going to be equal to 0.8 for this question. And that is from table 3.4. In AS 4100. So that's how you find your safety factor. Okay, let's put everything in. So our N star is going to be safety factor times NC. So we just found the safety factor 0.8. NC we found previously in the other question. That was 3082.25. That's in kilonewtons, so I'll just multiply it by 10 cubed to change it back to newtons. And divide by 0.4 times Fy, which was 350. And this should give you 17,163 millimeters squared. So basically what this means is our new, oh sorry, this is going to be the other way around. Our new AG has to be bigger than this area that we found before. So now you go back to one steel, and because we're now changing to a universal column, scroll down to the universal column page and find a section that has an area that is bigger than this number. So there are a few, it doesn't matter which one you choose. Normally you go like a little bit higher just to be safe. So we can choose the 310, you see 158, for example. So as long as you're choosing something with a bigger size, it doesn't matter. So this part is kind of up to you. So let's get the information for this from One Steel. So the new area of this section is 20,100 millimeters squared. Your form factor, KF, is 1. And your FY is 340 MPa. And we also want Rx, the radius, which is 139 millimeters. And these are all from One Steel. Does anyone have any questions so far? Okay. So they've told you that the new section has to have the same compressive capacity. So we want to check this new section and just check that it's okay and it works for compression. So what that means is we want to check this criteria. So we want to check that. So that means that we have to find the new NC. So we did all of this before in part B, so it's essentially the same thing. So we want to find AC, we want to find the reduction factors, we want to find the slenderness. So this time they've told you that buckling, in the question they've said that buckling about the minor axis is restrained. That means that everything in the y direction is restrained. That means we only want to check the x direction for this question. So you don't need to check two separate slendernesses here. So we can just calculate your slenderness using the same formula that we used before. And we have everything here from One Steel. Again, the effective length has been given to you. So they've said that the effective length in the x direction is 4 meters, or 4,000 millimeters. So the slenderness will be 4,000 over R, which was 139, times root 1, times root 340 over 250. And that would give you a slenderness of 33.6. Now we want to find alpha B again. So this is now from going back to the tables in AS 4100. Last time we used table B to find alpha B. This time we're going to use table A. The reason for that is our form factor, KF, is equal to 1. So before I told you guys there are two separate tables. One is for KF equal to 1, one is for KF smaller than 1. Before we use the one for smaller, this time we're going to use the one for equals to. So the type of section is a universal column. And from the table you can just read off that alpha B is equal to 0. So now we have our slenderness, we have our alpha B. Again, the slenderness isn't a nice number. So you want to interpolate between two numbers that are close to it. So 33 is between 30 and 35. So we'll just find the corresponding alpha C values for that. For 30, we would have alpha C is equal to 0.943. And for 35, we would have alpha C is equal to 0.925. And these are both from table 6.3.3c. from AS 4100. Same as before. And same as before, we can just use linear interpolation between these two numbers to find what alpha c would be for our question. So for a slenderness of 33.6, you would get alpha c equals 0.938. And again, this is just by interpolating. Any questions? Okay. Let's go back and find NC. So, sorry, NS. Formula for NS, same as before, is KFAN We have all of these things, and we can continue to use the assumption that AN is approximately equal to AG. So this will be 1 times 20,100 times Fy, which was 340, which is 6,834 kilonewtons. So now we can come back and find NC, which is equal to alpha c times NS. So that will be 0.938, which we just found, times 6,834. And that gives you 6,410 kilonewtons. So now we want to check the compression capacity. So on the right-hand side of the equation, you have your safety factor times this. The safety factor we found before was 0.8. 0.8 times 6,410 is going to be 5,128 kilonewtons. And on the left-hand side, we have our N star. Before, we assumed that the N star is like approximately equal to safety factor times NC. So we will continue to use that assumption. Safety factor is 0.8. And the NC that we'd use here is the NC that we had previously, which was 3,082.25. So that gives you 2,465.8 kilonewtons on your left-hand side. So if you go back to the criteria, compare these two, obviously 2,000 is smaller than 5,000. Therefore, the criteria is satisfied and this section is okay. So you can stop here, but if you want, see how 5,000 is like a lot bigger than 2,000? If you want, you can go back, choose a new section, and retest it all again. You can keep doing this multiple times, as many times as you want, as long as the section that you choose in the end satisfies this criteria. So it's up to you whether you want to stop here or whether you want to keep going and find a new one. Do you want me to stop here so you have time? Yeah.
Yeah, sure.
Yeah.
What time's lunch? Maybe it's 12. I don't know.
Yeah, I'm happy to stop
That's
here.
right.
Yeah.
Thank you.
All good. Does anyone have any questions on the last part? Yeah.
Would we lose marks if it's too far off?
So this section here,
It's not the middle.
I don't know how strictly they mark, but
Yeah.
maybe.
Probably.
Yeah. But like once you've done it once, the process isn't too hard. So you can go back and do it again, hopefully fairly quickly. Yes. I would recommend like resizing maybe at least once. They like to see that.
All right, cool. All right, so just continuing from that same past paper, right? Basically, the second question, you get given a new section, and they're asking different things of you. So before, they were looking at there's like the tension and compression capacities of the UB/UC in Part D. Now we're looking at a welded beam section, so it's a lot bigger, basically, right? And they are interested in this beam in flexure basically because we're looking at like the moment capacity and the shear capacity. So yeah, basically they don't tell you what what loads are on it, but you're basically just trying to find the maximum capacity, right? So I've got like little snippets from one steel. Okay, what they want is My, MP, so that's your first yield moment. And that's your plastic moment. So basically, the lecturer is trying to see your like understanding of these concepts because you can't directly get it off of one steel, even though it's a standard section. So basically, he's trying to figure out whether you understand how to read the table and then translate it into these kind of like parameters, right? So for first yield, the formula goes like this, right? You've got the yield stress of the steel, and then it's multiplied by the elastic section modulus. So that's the elastic section modulus, right? And the plastic moment is the plastic section modulus. Okay, so first of all, how do you get Fy, right? So if your beam section looks like this, right? Basically, in the second page, so when you go on one steel, there's the first page which has all the geometric properties, and then there's a second page which has all like the material properties, right? So on the second page with the material properties, they'll give the yield stress, right? And then there's the yield stress of the flange and the yield stress of the web, right? And then sometimes these are different, right? So in the case of a 1200 WB, I think it was the smallest one. Basically, for the flange and the web, right, we have a different yield number. So the web, it's saying that at a yield stress of 300 MPa, that's going to yield, and the flange is at 280 MPa, that's going to yield, right? So what we actually do is we take the minimum. So you saw this bit earlier in Damir's part as well. So we take that as 280 MPa, and that's just the number that we're going to roll with for the rest of these calculations. Okay, so the elastic section modulus and the plastic section modulus are actually geometric properties, so they're not to do with the material yield. So you actually go bending about the x-axis, so the neutral axis of our beam is like that. You look here and you look here, and you have to also keep in mind that these numbers, whatever you see there, is multiplied by 10 to the power of 3. Okay. So for the elastic section modulus, you can see for the smallest 1200 WB, we have 10,900 times 10 to the 3. Don't forget that. I did that in my my practice calcs for getting 10 to the 3. And then for SX, you have 12,900 rather. Okay, so it's like that. Yeah, you multiply these together. And basically, you're going to get something in Newton millimeters, right? So you have to convert it to kilonewton meters, right? So when you do that, you get 3,052 and 3,612 respectively. Okay, so what I did, right, is whatever I typed on my calculator, I multiplied it by 10 to the negative 6 to convert it to kilonewton meters. Okay, so that's part A and B, right? You're just trying to figure out the yield moment and the plastic moment. And now we're asked what is the bending capacity of this beam if the effective length is 4 meters and the alpha m constant is 1. Okay, so MB is equal to this formula, right? So you got alpha m, alpha s, which is your slenderness factor, and ms, right, in the x direction. So first we're going to calculate ms in the x direction, right? And here we actually have to refer to ZEX. So ZEX is actually in the material properties part, so the second page of one steel. And you look here, okay? And the idea is it's a compact section. So you see that it's actually the same number as SX. Okay, so I'll explain what that means in a second. All right, so you plug in that number, multiply it by 10 to the 3. Yeah, so if you were to imagine this is like a little bit of a timeline, right, or like a number line. You've got your value. Okay, let's just put 0 here. Right, you got your value for z, and you got your value for s. Okay, so this is like an increasing number line, right? Z was 10,900 millimeters power 3. Sorry, that's 10 to the 3 as well. And then S was 12,900 times 10 to the 3 millimeters cubed. Okay. The idea is that if you have a compact section, your ZEX is going to be equal to your plastic section modulus. And the idea is that's the upper cap for if you have a compact section and it doesn't like locally flexually buckle. Okay. So that's what the C refers to. It means that this will mean that ZEX is SX. Okay. All right. FY, we're going to plug in the same number as we had before, which was 280. All right, and now we can just compute that. We get 3,612 kilonewton meters. All right, so that is going to go here. Okay. We're given in the question that alpha m is 1, so that's already sorted. But now we have to calculate alpha s, which is your slenderness reduction factor. So your slenderness reduction factor is the part that's the longest to calculate, right? And we're told in the question that LE is 4,000 millimeters. Now, like sometimes you're given it as just L, right, which is the original length of the member. And then you have to multiply it by all these factors like KR, KT, KL, whatever. Here we don't have to do that. So luckily he just gives us LE. So you don't have to compute all those different properties. And that number's going to go plug into this equation at the bottom of these fractions. Now, you have to collect all these other terms, and these are also from one steel. And so these are geometric properties, as well as we have some material properties too. So material properties are always going to be consistent in this course. So material properties for steel, we take in this course as 200,000 MPa and 80,000 MPa, right, for elastic modulus and your shear modulus respectively. And that's going to stay consistent, and that's just like a factor they put into AS 4100, right? For your moment of inertia in the y direction and your warping constant and your torsional constant, these are numbers that you can get from one steel. So you just got to be really careful about what it's multiplied by, because how it's presented in one steel is a little bit like difficult to read. So first one we need is IY. So that's your moment of inertia about the y-axis, right? So that's 87. And then you also have to make sure to multiply 87 by 10 to the 6, I think that says. Yeah, I had to double check as well. So that's one. Another one you have to get is, sorry, this screenshot, I did it in two parts, right? So the right-hand side of the table is here, okay? So it's a 1200 WB, the smallest size one, right? Your torsional constant is 4,310, but then you have to multiply it by 10 to the 3, right? And then your warping constant is 28,500, but then you have to multiply it by 10 to the 9. Okay, so just be really careful with these, like what power of 10 you're multiplying it by, because it's very easy to make a mistake here. Okay, when you're typing this in your calculator, more often than not, you're going to run out of space. Like the calculator can only store so many numbers before it just shits itself, basically. So what I would recommend that you do is that you compute this fraction and then store that on as like A or something in your calculator, and then you store this as B into a calculator, and then you type in square root A multiplied by B, okay, and then that'll give you your MO value. And then I would also store MO for later, because you're going to need MO in the next step, so I'd store that as like C or something maybe. Okay, so these come with practice, right? But in your exam, this is like make or break, because you have to do it very quickly, right? So I would get used to that very like, yeah, I would get used to the routine of going through typing all these things, okay? All right. I don't think anyone's still copying. Okay, so now I have to calculate alpha S, right, which is what we're looking for. We just found MO, okay? And then in the earlier part, we found MS or MSX. What I would actually recommend that you do is maybe you store, let's say on your calculator you store MSX as D, right? Then you can just do the fraction of D on C. So inside this bracket, you would do bracket D on C squared, and then for this one, you just do like D on C or whatever. Anyway, it's very easy to make a typo on your calculator as you're computing these, so just get used to doing that. Yeah, I've been yapping a lot, but I need to flip pages. I've got my notes printed out. Okay, so the actual numbers that we're plugging in, right? So MS from earlier was 3,612. Okay, so normally you have to think really hard about whether you've got something in Newton millimeters or kilonewton meters or whatever. But because this is a ratio, right, of MS to MO, as long as they're in the same units, you're fine. Okay. So your reference buckling moment, let's say that you got it as, did I compute it earlier? Sorry, I didn't. Okay. Basically, that one was 6,437.33. Okay, and that's what you would store to C or whatever on your calculator, right? And that's in kilonewton meters because I would have computed it and then multiplied it by 10 to the negative 6 to get it into kilonewton meters. I'm getting a call on my phone. It's a scam call. Okay. All right. So now we just replace these numbers. Yeah. So we get that as 6,437.33. Same thing with this number, right? Okay. So doing all that, you get that alpha S, our slenderness reduction factor, is 0.756. Okay. And that's basically what we were looking for. So now we can just plug it in. Okay. So we're going to reduce about 25% of the capacity because of the slenderness. And then MS was 3,612. Okay. MB is 2,729.73. And you just have to double check that this is less than the section capacity. The section capacity is basically, imagine like a glass of water, right? The size of the glass, or how much water it can hold, is MS, right? And then MB is how much water you actually pour into it, okay? So you can't pour more water than the glass can carry. Do you get what I'm saying? Yeah. Okay. Okay. So next, the question asks, what is the? Let me go back up. Okay. It asks, what is the shear capacity, right? So what we're looking for is VV. Actually, we're looking for VVM, right, which is accounting for the interaction between like bending moment and shear as well. If the design bending moment to moment capacity is 0.75, the wording's a bit funny here, but basically what it's trying to say, one sec, let me just make sure the values, I'm typing it all right. It's trying to say that M star over phi ms is 0.75, okay? So that's to do with your shear interaction, right? Okay, but the idea is that we're just going to look for VV first, okay? So VV is basically, like to get the shear capacity of a beam, you have to go through all of these like linear steps and checks, okay? So the first thing we do is we find the shear web capacity, the web's yield capacity in shear, okay? And so it follows this formula, okay? So it's 0.6 multiplied by Fy. Now, Fy was the web's yield capacity. So, oh wait, no, it wasn't. It was the minimum between the web and so this is the minimum between these two, okay? So we're just going to still take it as 280. So this isn't the yield capacity of the web specifically, it's the yield capacity of the entire beam section, okay? AW, right? Now, I got this wrong in my notes before, and someone corrected me, okay? So this is important, keep this in mind. All right, I'm going to draw it out. So this is your beam, right? AW is this area, okay? It's not this area. So you want to get the entire depth of the section, right? So D, multiplied by the web thickness, okay? That's actually how you compute AW. So it's ambiguous in the code because it just says find the area of the web. But when you look through any of the work solutions, they take the entire depth of the beam. So you include the contribution due to the flange as well. And that's how you find like the web capacity, okay? Or the web area rather. Okay, so we're gonna multiply it by the thickness of the web. So that's 16, as well as the depth. So that's 1,170. Okay. So computing all that and then dividing by 1,000 to get it from newtons to kilonewtons gives us 3,144.96. One sec. I'm getting really warm, so I'm going to turn on the aircon. One sec. It gets too cold or something. Okay. All right. So basically, now we've got the web's yield capacity, right? What we're going to do next is we're going to check the web's buckling capacity. So the idea is you got the shear happening on the web, and if this web is too thin, right? If it's like that, there's a chance that it buckles. I'm running out of colors, right? There's a chance that the web buckles. Okay, so we're going to check the buckling capacity, and so we're essentially doing like a web slenderness ratio check. Okay. So this is the formula for an unstiffened web, which means there's no plates here that are stiffening it. So essentially, we get what we got in the first step. Let's call it step 1, right? So this is step 1. And then we multiplied by alpha V. So alpha V has this formula, okay? And we're just plugging in these geometric values that we know. Okay, so dP, this is dP, it's the depth of the panel, right? And that was 1,120. And you divide that by 16. You put that in the bottom of the fraction. You get Fy, which is 280. Okay, and then alpha V is 1.225, okay? Basically, since that's greater than 1, and this is supposed to be a reduction value, a reduction factor, it can't increase your capacity, right? So you set it back to 1. Okay, so therefore alpha V is 1. So alpha V goes into this equation here, and this was from step 1, right? And so this is 1 multiplied by whatever you got in step 1, and that gives us VB. So VB is our answer for step 2, okay? All right, so now for step 3, right, this is from my notes. There's 2 scenarios. One is if your web panel doesn't buckle, then it yields. But if your web panel does buckle, then you take the buckling capacity, right? But here it doesn't matter because step 1 and step 2 are the same. Okay, so either way, your VU, which is your step 3 value, is the same. Okay, so that's VU. And then step 4 value is to do with how uniformly distributed your shear stress is, right? So on your beam, if you map the shear stresses out, it might look something like this, right? Basically, the idea is you're looking at the web portion of it. There's like a max, okay? So let's say that's shear max, and then there's some value for shear average, okay? If the ratio of the max to the average is less than 1.1, then you have a uniformly distributed, approximately uniformly distributed shear distribution, right? And therefore, you just use this formula, which is step 4 is equal to step 3. Okay, the reason why I didn't do all that is because in the lecture notes, it just tells you that for WBs and for UBs, you can assume you've got a uniformly distributed shear, basically, right? And so we don't have to actually do that. I'm just giving you that for context. And so yeah, basically step 4 ended up being whatever we got in step 1 anyway. Okay, so if I go back to the question and how it was worded, right? We said it said that the ratio of the design bending moment to moment capacity is 0.75. Okay, so we can use that information now, right? Because, right, so again, this is a snip from my notes. So if that ratio is 0.5, then it satisfies this criteria of if your moment is less than or equal to this number, okay? Then we basically just set, let's call this step 5, okay? Your value VVM, right, is equal to what we got in step 4, okay? So we're just setting all these like steps equal to each other. It's a very like linear like set of checks essentially, right? What we're doing. Okay. All right. So now we have to play around with this formula because, wait, do we? Not really. Okay. We basically just find that this is our web capacity. Okay. And so our value for step 5 was basically just ended up being what we got in step 1 anyway. But we had to do all those checks just to make sure. Okay. Right, so that's question 2. Do you guys have any questions about this question? Yep, Andy?
So you can skip step 3 if in step 2 VB is equal to VW, right?
Yeah, basically, yeah. Because, have you seen that meme that's like, there's like a cow, and it's like looking, and then there's like 2 paths that he takes in this maze, and it leads to the same like scenario in the end? It's like, no matter which path you take, you get the same answer. That's what I'm trying to say, right? Yeah, so it doesn't really matter. So yeah, basically what you said is correct. Okay. Any other questions? Yeah.
How do you know that VB is the same as VVM?
So it basically I basically stole this from lecture slides, right? So if you have this criteria that's satisfied, then you can set step 5 to step 4 like what we did. But if the criteria is not satisfied, you have to apply this little like reduction factor thing. Yeah. And basically we were told that that is 0.75 phi ms or whatever, right? Yeah. So we're given that in the question basically, yeah. Okay, any other questions for now? Nope, okay. So now we're going to move on to question 3. Question 3 is, this is just data for it. I'll just scroll back up to it later. Question 3, you get a different section now. So you get a welded column. And basically, so you can assume that this is in a column system of some sort. All right, the wording's a bit funny, right? So let me just look at my notes real quick. Okay. What is the maximum design bending moment, right? If the ratio of design axial force to section capacity is 0.5. So that basically means we know this. Okay? So we just have to manipulate the formulas that we have for like combined actions in order to figure this out. And then part B is similar, but it's what's the design bending moment, this is in blue. What's the design bending moment in the minor axis if the ratio of design bending moment about the major axis to capacity is 0.75. Okay, so that one means this. Sorry, that's subscript x. Okay, that one's equal to 0.75. And the design axial load capacity is 0.6, okay? Okay, so okay, I'll show you what this means as we go, all right? But let's do the first part first, right? So we look through our formula sheet and we find this formula, which is talking about the reduced capacity, okay? First thing we've got to do is we've got to compute the section capacity, right? And we were given that this was 0.5, okay, from the question. So that's this bit of information, right? So we just got to find this first. Where you find that is you go to one steel, and then you find ZEX, right, which is on the second page, and ZEX is 10,400, right, for 300 plus steel. And the yield strength is 280, Okay, so that's Fy. This one ZEX. Right, and don't forget to multiply by 10 to the 3. And then also I want to show you, this is the table of capacity factors from 4100 as well. And for members subject to combined actions, we're taking 0.9 as well. Okay. All right, so we have all this information now, we just plug it in. Okay, and then Fy is 280. All right, that gives us 2,912 kilonewton meters. So again, this involved dividing by 10 to the 6. All right. And we can use that number and plug it in here. Oh, sorry, I've done it in a new line. Okay, so 0.9 was the phi value. Okay. MS, which is what we just worked out, is 2,912. So this will give us a value in kilonewton meters, right? We do 1 minus 0.5, which was given in the question. Okay, and this gives us the maximum moment was 1,310.4 kilonewton meters, right, of bending moment that could be applied. Okay, so like physically, I guess what this looks like. I'm going to duplicate this because I'll talk about this later as well. Is we've got some kind of axial force, and let's say bending in the major axis direction. Let's put it like that. Okay. We just figured out the value for mx. Okay, and this like column section, it had like inherent properties of ns. Okay, and it also had phi m. What is that? I guess MSX, okay? So these, yeah, anyway, there's like some trickery with the ratios going on because these were paired together, basically, right? So we just worked out what the max bending moment that we could apply onto the column was, essentially. Okay, so for part B, right, so let's reread part B. What is the max bending moment about the minor axis, okay? So now this time, instead of bending along this column's major axis, we're doing it about the minor axis like that. Okay, so now the bending moment's being applied this way, that way. Oh, wait a minute. Applied this way. Okay, so it's causing it to bend about its weak axis. Okay. Given that we still know, some kind of other actions are being applied. Okay, so the idea is that there's also this direction bending, and there's also an axial force as well, of some sort. Okay. Anyway, so what we do is we look at our formula sheet, right? So this is a snip from my notes, and we know that ultimately we have to get to this equation, right? But in order to get to this equation, we have to look at this one, okay? Because this one's basically given to us based on the question's wording. So this equation here is what we're gonna work out next, okay? So in green. So we had to figure out MSY. So what is the section's bending capacity in the YY direction, or its weak direction? We do the same thing as we did before. So we find Fy, which was 280. But now this time we're looking at a different part of the data sheet. We're looking at this one, right? So bending about the YY axis gives us 5,010 times 10 to the 3, okay? So that gives us 1,402.8 kilonewton meters, all right? So using that number, we can plug it into here, all right? And basically here, okay? We know from the question's wording that this fraction ratio thing was 0.6, okay? So we can just plug that into the brackets, and that gives us, right? That gives us 0.9, which is the phi value, right? Times 1,402.8, multiply by 0.4, okay? So that's 1 minus 0.6. Give me a sec, I'm trying to figure out where I am. Yes, that gives us 505.008 kilonewton meters. All right, so now with that value, we can plug that in the bottom of this fraction. Because in the bottom of this fraction, so where I got this equation from is it's this one. Okay, so this is the biaxial bending formula, right? So like we can basically work out my, which is what we're looking for, right? Because my is on the top of this fraction, right? Its capacity we've chucked here. And we were actually told in the question that this ratio was 0.75, okay? So you put 0.75 into this bracket, you multiply it by you put it to the power of 1.4, and then you basically just rearrange this equation. It looks like that if you solve for my. And you get 229.514 kilonewton meters, okay? So that's the amount of, that's the maximum amount of bending in the y direction that you can apply onto this column before it breaks, okay? Yeah, so yeah, that's basically all that. Yeah, Andy?
You know the axial load ratios of the question gives, like 0.5 and 0.6?
Wait, could you repeat that, sir?
The axial load to the section capacity.
Yeah, it was given, yep.
How do you know which one is which? Because for the first part, it's n star over phi n s, but for the second part, it's n star over phi n 2y.
Yeah, so it's kind of funny because the wording's like hard to understand. So you have to do it based on context, okay? So if you read this, right, ratio of design bending about the major axis to capacity is 0.75. Okay, let's just break that down for a second, right? So ratio means you have a fraction, right? Design bending about major axis, so like a design bending moment is like your m star thing, right? And about the major axis implies x, like subscript x, right? And then to capacity ratio, right, means phi m something. So contextually, you have to figure out what the capacity that is relevant to you is, right? In this context, it's the it's like I think this is called like the in-plane bending capacity of the member about the x-axis or something like that, right? So this is the one that's relevant to this particular formula, and so then you find that that is equal to 0.75. And you do the same thing when you're looking at this, right?
So yeah, so you just basically look at what you need, and you're like, okay, that fits.
Yeah, pretty much. Yeah, like the first time you see it, it's like it takes a second to wrap your head around. So I would just say, like, take some time to digest the sentence, and then you won't be super surprised like in the actual exam itself. Okay, so I've kind of run out of time because you guys got to have lunch, but I did prepare a little bit of extra, but I'll just run through, like I'm not going to write like what I did again. What I'll do is I'll just duplicate what I had prepared for the last bit and just show you. All right, so here is, basically in my drive, in my Google Drive, there's this like textbook, right? And it's called the Steel Designer's Handbook, right? And it's a really good resource because it explains a lot of things that are in the standards, right? But the problem is it's from 2005. Yeah, so it uses the old standards, right? So AS 4100, whatever it is. I don't even know what it is, right? But we want the most recent standards. We want the 2021s, right? And so some of the values that you're going to see in it are from the old standards, including like material properties and stuff like that from table 2.1. So you can use the questions and the steps because all the steps don't change, but some of the values might like move around a bit. But you can use this as a resource to see all like different varieties of questions, like step-by-step solutions of them, etc. So here I've got one. So this is example 8.1. And it's a similar question to question 1 from the 2025 paper that Damien ran through. But it has like a few extra checks that may or may not be in your exam, right? But I feel like lecturers love to like find a little trick to make sure you're paying attention to like every little bit of the lecture slide. So I'll show you the little trick that's different to what you might be expecting from like other past papers. Okay, so here they've collated the data, right? So what's happening here is if I take a section, let's do that in blue. If I take a section, A to A, right, it looks like this. So we've got, what you can see is the plates, right? So these are the plate members, and we've got like a twin splice plate thing. So let's do that in purple. So this is on both sides, right? The reason you can tell it's on both sides is it says there's 2 splice plates. So that's these things on the side, okay? They're connected with these M20 bolts, like as you can see basically, right? And then the member's intention. So there's a couple, like if you weren't told exactly what to check for and they just say like, check everything, right? So here's the specific checks you should do, okay? The first thing you gotta do, the first thing you gotta do is you gotta figure out like the gross area of these things, as well as the net area. So you minus off the bolt area, which is like that's like that basically. And then you got to go to the standards, right, and look at the FY values and FU values, so the yield and the ultimate strength. And so you've got all the data in front of you, right? Similar to that first question that Damien ran through, you check the yield and you check the fracture for the member tension. So that's the member, right? So that's the thing in blue, okay? And then you got to check it for the splice plate as well, okay? So that's these ones in purple. Check if they're going to break in yield and in fracture. And then you got to check the bolt shear, okay? So that's similar again to, I think it was like part C of the first question that you saw. But here we've basically got 3 layers, okay? So 3 members being like tied together. And we actually have 2 shear planes, right? So we have 2 shear planes here and here, okay? So there's that formula, right? So this is from, again, my notes here. And you got like NN and you got NX, right? So that's for the case with the shear planes running through the threads and without the threads. So if I were to draw this detail and enhance it, right? Let's just draw it bigger. Because I'm going to draw the bolts themselves, okay? So the bolts might look like this. And then here might be the nut that ties it together, right? And you might have washers, okay? The idea is if the bolts themselves, so this is the core and the core and the threads, right? So essentially, if your threads go like that, okay, you have 2 shear planes where the core area, which is smaller, right? You have 2 shear planes where the core area runs through where the shear planes are, right? So that's one potential scenario, okay? Another potential scenario is if your threads only start over here, okay? And then technically you would have, you know, a shear plane where you've got the larger cross-sectional area, like that, versus a smaller cross-sectional area like that, okay? And yes, like, if you had that second scenario, so let's say that's scenario B and that's scenario A, right? If you have scenario B, then this would be 1 and 1. If you have scenario A, you go 2 and 0, okay? So it's more conservative to take it as scenario A, where every single shear plane that your bolt runs through has the threads going through it, because you don't want to design something that is like not robust, you know what I mean? If the tradies buy like a different bolt that has the entire thing as threads, and then your member fails because of that, that's on you, you know what I'm saying? Like, you want to take the more conservative approach when doing this. Anyway, so that's basically why, I think you had that question earlier, right? That's why you would set this as 0, right? So NX would be 0, right? And so you get this as your fastener's shear capacity. And so if we check it for 4 bolts, so what I'm looking at is, oops. Okay, there's kind of like, if you think of the load path, right? You've got your load, and it goes from the member to the splice plate, and then you have another interaction where it goes from the splice plate to the member, right? So we're only checking for 4 bolts because in a single like interaction, there's only 4 bolts happening at once, right? Like as the load's being transferred. Where was I? Yeah, so we don't do 8, we do 4, okay? And it's actually going to fail if you take n x is equal to 0. The solutions in the textbook actually assume one shear plane that passes through the core and the one that passes through the shank, but I wouldn't do it like that, to be honest. Okay, now here's the part that you probably haven't even seen like a work solution for, right? Applied tear out. So it's in my notes, right? But this worked example goes through how you would apply that, right? So the idea is if you've got, I've actually got balsa wood from Desmond 1000. There's like some groups that basically gave me their spare. Yeah, so if you've got, let's just say there's 2 boards, right? Instead of 3 boards, okay? If I had my pen and I like jammed it through, right? Let's say I jam my pen through here, okay? If my pen was too close to the edge of the board and you pull it, the board itself would split and tear out, okay? So that's ply tear out. And there's another similar idea for ply crushing, okay? So you're actually checking the member itself and checking whether the tension force is going to destroy the member due to the bolt. Like it's kind of weird. It's like an in-between check between whether you're checking the bolt or the member, right? So you're checking the edge distances and stuff, essentially, right? So with that said, you have to account for the splice as well as the, well, I'm going to go out of my thing because I can't undo. Which one was it? Okay. You have to account for the splice as well as the member itself, okay? And for the splice, all the calculations will be taking 2 layers into account, right? Okay. So first thing we're going to do is we find, by the way, for both the splice plate and the member itself, we have the same ultimate, so this is like FU in the standards, the ultimate member tension capacity. Okay, so they're the same. Next thing we're going to do is check the edge distances. Right, so when you look at a given bolt, right, you have to check this distance, which is 35, and you have to check, it's supposed to be from the edge to the middle of the bolt. And you also have to check the bolt to bolt center to center distance as well. Okay, and you take the minimum between those two. Right, and that's 35. And you also take the thickness of the plates, okay? So the first thickness you would check is 20, okay? And the second thickness you would check is 2 lots of 18. Because the 2 splice plates are always going to be acting together, you basically have to account for the thickness of both of them, all right, before they rip out. Anyway, so the minimum of that would be the member itself's thickness, which is 20. Anyway, so you plug all these things into this formula, right? So this is your ply tear out capacity. You multiply it by the ultimate steel stress, and then you get 301. And basically what you have to do is, like, you aren't checking this. So here's the weird part, right? Because you're using the member itself's material properties, but you're checking how much force is being applied through one bolt, okay? So because all 4 of these bolts are kind of moving in tandem, the idea is you essentially divide whatever load you had by the number of bolts, right? And then this is how much force is going to be applied, let's say, locally here at 1 bolt, but then you're checking that versus the member's tear-out capacity. Does that make sense? So it's like a very strange check because you're doing like 2 different kind of things. Anyway, so it's actually, yeah, it's good enough. And then ply crushing is very similar. It uses like similar values but it has like a different formula, I guess you can say. And then this one's fine as well, because you're using the diameter of the bolt for the crushing. Anyway, yeah, okay, that's all we had. So do you guys have any questions about the crushing or the tear out or anything like that? One more thing I'll note is the lap distance. So yeah, Damia mentioned and talked about this formula in her part, right? But for this part, KR, so the reduction factor for lapped connections, if you look at this question and the setup, right, you might initially think that you're taking the lap distance from here to here, okay? So this, it doesn't even give you all the dimensions for it, like it doesn't give you this dimension here. And you might think, oh, that might be bigger than 300, right? But in reality, we're looking at the interaction at one interface, okay? So between the splice plate to the member. And so therefore, we only need to check the lap longitudinally between these two rows of bolts, like longitudinal rows of bolts, okay? So we're just taking that as 70. And essentially, since 70 is less than 300, we take a reduction factor of only 1, okay? So yeah, that's something else to consider. Okay, any other questions? Yep.
AC and AO, that's always from the table in
It's, did you say in AS 41?
1275.
Yeah, I actually didn't know that, by the way. I just took it from the lecture slides.
I researched so much for it. Yeah.
Yeah, it's from a different standard. That's not AS 4100. That's pretty cool though. But yeah, you take it from a standard set of, because like these they're like Legos basically, right? All these bolts and all these members are like, the sizes of them don't change. They're standardized products similar to Lego, right? And so you always know the cross-sectional area and whatever that you take, right? Yep. Okay. Any other questions? Okay.
And,
Yep.
bearing stiffness will be tested.
It's not out of the question. I'm not going to say it's not going to be tested because it could be tested. Yeah. All right, cool. Thank you for your time. Oh, thank you. Oh, yeah, thank you, Damia, as well. Thank you. Yeah. All right, let's have